finish the proof real close to the end of class. Let's even just summarize the idea of where we are. So there's what the theorem is. X be a figure, f of x is directly bounded, then for every epsilon there is some delta such that for every subdivision whose mesh size is less than delta, the distance between the lower integral and the lower derivative and the upper integral and the upper derivative are both less than x. And this will be useful in that it allows us to, instead of say, well, just find some subdivision for which those two things are close, we can arrange that the subdivisions are as close as we want to the actual integral, just getting the grid size. So let's summarize where we were so far. So the first thing we did is we found like a seed subdivision. Delta 0, such that the integral and the corresponding derivative sum, and you'll notice that I left off all the decoration. I left underlined minuses over overlined pluses. And we decided that epsilon wasn't actually good enough, so we divided that by 2. And then what did we do? We appealed to something about this subdivision. So if that subdivision, let's draw a subdivision. For that, then on a fixed arbitrarily small epsilon we chose, we can find a subset of each element of that subdivision, find a smaller subset, I think we call it I prime. The original one was I. Yeah. So if that's one of these i's, we found an I prime. So that I prime takes up almost all of the volume of I, but so that there exists a positive number delta. So that if you take any point in I prime and take a delta neighborhood of that point, all of that will be inside of I. So what did we get? We saw that for every I in delta, there exists an I prime and a delta sub I such that for every x in I prime, the ball centered at x of radius delta is contained in I, and the volume of I prime minus I is as small as we want. That's what we did. And we played some more bookkeeping games, like we said, let x be the union of all of these I prime minus i's. X prime, x double prime? X double prime, I think we called it. So then what was the game? So then we said, well, let's see. These are all delta i's. We took delta to be the min of all of these delta i's. And we took some subdivision delta whose mesh size is less than that positive number delta. And then by just drawing a picture, you can see, I guess delta prime was then so definitely we know that this subdivision does a good job approximating the integral because it's a refinement of a subdivision that did a good job approximating the integral. So then we wanted to decide, well, how big is s of f delta minus s of f delta prime? Where here I again have got all the pluses or minuses, put the right one back in. Because if we can show that, then we'd be done. Now, if we study this difference, let's draw a picture of an element of delta. So here, let's draw some j in delta. Now, all of these j's have mesh size less than that numbar, little lowercase delta. So that's something worth remembering. So let's draw a picture of that j. Let's suppose so here's that I that I drew above. There's I prime. So what did we notice? We noticed that as soon as j had a point in common with I prime, then j had to be a subset of I. That sounds familiar from last time? So if there's a point P in j that happens to be inside of I prime, then I have no idea what j looks like, but I know that j is contained in I. So as if j is a subset of, nope, if j intersect I prime is not empty, then j is a subset of I. But what's the point? Why is that something that's useful if we want to think about that sum? In this case, j intersect I is equal to j, so j is also an element of delta prime. So all of those terms of s in this will cancel. So that means we can rewrite these sums a little bit. So instead of writing I'll write it down for s minus. Actually, I think this is about where we were at the end of the notes. So maybe I should just move over to the notes. I'm going to move over to the actual notes. Nice. So let's write out this sum. So s minus of f delta minus s minus of f delta prime. All right, we already know what that is. That's the sum of all of these things that look like m of fj times the volume of j minus the sum of all things that look like m of fj times the volume of j. And you could cancel a bunch of these terms. So remember, x double prime was the union of all of these I minus I primes. That's what we called x double prime. And what terms can we cancel from here to there? We can cancel any j, which is we can cancel the term corresponding to any j, which is simultaneously in delta and in delta prime. But, so we can cancel each term that corresponds to some j which is properly contained in one of the i's, because then that j will be in both delta and delta prime. Now the only way that that can fail to happen, so the only terms that you can't cancel by the argument we sketched, is properly contained in x double prime. So that means we can cancel all of the j's, we can cancel all the terms corresponding to a j which isn't a subset of x double prime. So let's do that. So I'll just cancel those terms, so the actual sum ends will stay the same. So I think that I will just try to convince you now that we should be convinced that this proof will work out. So now I'm only adding up things that are subsets of this x double prime. And remember, the x double prime was like everything that's not in one of these red pieces. That's it. So can I do this so that the volumes of the complements of all of those red pieces are simultaneously tiny? Yeah, that's this, right? By choosing delta appropriately, I can make this very small. Well, but there are also only finitely many things to it. So if I can get this to be like less than epsilon divided by the number of atoms, I can get the volume of x double prime to be less than epsilon. So this will be adding up a bunch of m's times volumes, and the sum of all of those volumes will be less than the volume of x double prime, which is as small as we can. So that should be compelling that this will probably work out okay. But if all of these things are simultaneously small, I can be sloppy and just appeal to the triangle inequality right now. So let's do that. The triangle inequality says that I can distribute the absolute value to each of the terms, and in fact that minus will become a plus. So cool. So let's see. It's annoying that the m of fj isn't constant in the sum. But I remember what big M is, right? What's big M?
Maximum square root of the absolute value of x.
Yeah, I think we can use stuff like this somehow. But that would be like the best one that we could use.
Oh, yeah.
But yeah, let's make it be the super. Because that will give us the best control over the lowercase delta. So this big M is an upper bound on the absolute value of f. So all of these, even in absolute value, will be less than or equal to capital M. So this will be less than or equal to capital M times the volume of J, plus the sum of a bunch of things that look like capital M times the volume of J. Doing some factoring. But I could factor all the M's out, right? Are all of the various J's in delta disjoint? Effectively, right? Their intersections have no volume. So that means the volume of a union is the same as the sum of the volumes as long as the pairwise intersections allow no volume. Okay, are we happy? And remember, this x double prime is a set that we can arrange to have volume as little as we could possibly want. We didn't figure out how small we needed the volume of x double prime to be, but we can make it be as small as we want. So with that in mind, that union, is that obviously a subset of some particular set that you know that has small volume? Yeah, which one are you thinking of? Is it wrong or anything, or are you just wrong?
I petted a dog at the library, and I'm quite allergic to dogs.
Oh. You have my sympathy. I'd have probably done the same thing in your place. Oh, cool. But now, like, it's super easy. That's just 2 times m times the volume of x double prime. Okay, nice. So let's take a step back and see what we've done. We right now have the difference between s minus of f delta and s minus of f delta prime is less than 2 times capital M times the volume of x double prime. That's what we've arranged. What did we, so if we flip back to the previous page, what is it that we needed the difference between s minus of f delta and s minus of f delta prime to be? Less than epsilon over 2. Do you think we could, like, set this equal to epsilon over 2 and figure out some stuff from there? So if we want this to be true, shoot, let's go with less than or equal to. That would also make me happy. Do you think you could solve that for the volume of x double prime? Right, of course you can. Do some division. So let's go, here's something that's just aside, this isn't part of the formal item. Volume of x double prime, it looks like we want that to be less than or equal to epsilon divided by 4 times capital M. So now let's go back previously in the proof, because early on we left blank how small we needed the volume of x double prime to be. Now we can put that back. So here, the volume of x double prime. So apparently we want that to be less than epsilon. So we can put anything underneath there. Epsilon divided by 4 times capital M. And what did we do? We said, well, okay, volume of x double prime is less than or equal to the sum of the volumes of all of the i's minus I primes, that is the I double primes. We could make each of them simultaneously as small as we want. So all of those added up to an epsilon that we got to pick. But there are like some number of them. How many of them are there? There is one from each element of the set delta 0. So what do you need to divide by to arrange that this is equal to that? Well, I don't this exact same denominator, but there's a number of things in delta 0 in it also. Yeah. Right, so now we're at like the easy part of the proof where you like go back and try to fill in the blanks. 4m times the number of things in delta 0. And why did that happen? That happened because the volume of I minus I prime was less than something that we got to pick. Namely, it was smaller than, well, everything here except for the delta 0 in the top. So what do we need in this blank? We need epsilon divided by 4m times the number of elements in delta 0. Cool. So let's just see that we've now completed the job. Because like, we're pretty confident that the proof is complete now. All of the ingredients are in play. Similarly, I guess we can arrange that this is less than epsilon over 2. So by the triangle inequality then, the difference between the lower integral and the corresponding lower sum is less than or equal to the lower integral of x dv minus s minus of f delta prime fair enough. Do we have an explicit upper bound on how big that first absolute value is? That's an integral symbol poorly drawn with an underline because it's the lower direct row integral, followed by an x in the subscript, which is also Herculean. It's supposed to be this. Yeah, it's just a triangle inequality. So, this first piece, do I have an upper bound on how big that is? Epsilon over 2, that's like on the previous page. That's because delta prime is the refinement of delta 0, and we picked delta 0 to have that be small. So I guess this next bit always has to be less than epsilon over 2 also, is it? Yeah, that's like exactly this big long computation. Similarly, I claim that it's similar, and probably you believe me. The difference between the upper integral and the upper sum is less than epsilon. That seems believable that the exact same proof should walk. Yeah, that better be S plus. Nice. And I don't know. I've got some time. Well, this is just that. It better be if we want to compare it. If we want to compare something to an upper integral, it better be an upper sum. Ah, okay. Ah, okay. You thought it was like and in conclusion.
Yeah.
But let's just take a look at even this stuff, this line, and see if you believe that that should be the same for the upper integral. If you replaced that with upper integral, you would get that same expression on the right, but with capital M's instead of little m's. So you would get the exact same expression there, but with capital M's instead of little m's. The exact same cancellation would happen. You would cancel all of those common terms to get the exact same thing, but with capital M's instead of little m's. Is big M of fj less than or equal to the thing that we call big M? Less than, that's what I approximate. Yeah. And from there, it's like literally, it's the same expression. So yeah, the same proof done. Cool. So I think this is a good use for the remaining 25 minutes. I feel like I've been giving you guys lots and lots of work, and this class has been going very fast. I had the anticipation that we would use the whole class time to finish the rest of that, which is why I talked so much. But you guys have lots of things like benchmarks and, well, I guess just one problem this week. This is a good time to walk out of this. I'm even here if you want to ask some questions. Those of you taking the GRE, if you want to like go stressing about the GRE, I'm not going to be offended if you two walk in. You know the GRE?
So, no, the plan is better.
Okay. I guess my question, there's no judgment.
No, I know. I've talked to you about my plans, and that's.
Oh yeah, you did.
Yeah, I'm well now, but I would.